Hello, dear chemists. Welcome to this wonderful discussion where we are talking about chemical kinetics, and we are basically going to be modeling this process. So we have a scenario in the production of sulfuric acid, the oxidation of sulfur dioxide. Sulfur trioxide is a critical step. So we have two molecules of sulfur dioxide reacting with one molecule of oxygen gas to produce two molecules of sulfur trioxide gas. This reaction is catalyzed by vanadium pentoxide and follows a second order rate law with respect to sulfur dioxide, and the first order with respect to oxygen. So we are saying this is a three order or the third order reaction. So third order reaction, the total order of reaction is going to be 3. So it is a second order with respect to sulfur dioxide and first order with respect to oxygen. So if I get this 1 on oxygen plus the 2 on the concentration of sulfur dioxide, I get 3. So this makes it a 3 order or third order reaction. Now, to develop this model in Python, we are going to open VS Code or Visual Studio Code and right away begin the process. So to make this lecture or discussion brief, I've already provided a frame of this code, and then we are going to go step by step, updating it and talking about the meaning of each line. So right away we shall begin with importing the necessary libraries, and one of the important libraries in data manipulation is called numerical Python. So that is NumPy that we shall import as NP. Then we shall also need matplotlib.pyplot since we are involving a plot of the simulation on a graph. So we shall import matplotlib.pyplot as PLT. Then now we need to define the function of the reaction. So this function def, this is the function definition. This function is going to be rate of reaction, which takes 3 inputs. First of all, when you look at this, you have the K, which is the rate constant, the concentration of sulfur dioxide, and the concentration of oxygen. So these are the 3 inputs to the rate law. So that is the rate of reaction, and therefore we are going to put concentration of sulfur dioxide and concentration of oxygen. So let's also put concentration of oxygen. We put concentration, actually we put the rate law, which is, rate constant K. So this function must return, so the output of this function is going to be K times the concentration of sulfur dioxide squared times the concentration of oxygen. Therefore, we are going to have the concentration of sulfur dioxide times K. Obviously, this sulfur dioxide is going to be, the concentration of sulfur dioxide is squared. Then we are going to multiply by, the concentration of oxygen. So that is going to be the output of this function. So we are through. So let's initialize the values. A is told to be, or assumed or taken to be 0.02. The sulfur dioxide concentration is 0.5, that of oxygen is 0.3 in moles per liter, and the other one is in liters squared per mole squared per second. So let's look at the reaction rate for the given concentrations. So let's look at rate. Rate here is going to be, first of all, we have been given the concentration of sulfur dioxide. So let's take rate as a function that is receiving sulfur dioxide concentration as an input. Then we are also going to be receiving oxygen concentration. So once we compute that, what we are going to output is actually we are going to use a printed format. So the formatted string literal in Python is this F. So we are going to use it. First of all, we have a string. We want to print out something that looks like this. The reaction rate for sulfur dioxide is equal to a particular value. The reaction rate for oxygen is equal to that value. And we are going to produce this. Of course, this is going to be a float. And the rate is going to be given to 4 decimal places. So what we are going to do, we are going to put, first of all, for sulfur dioxide, what is the rate? So, I mean the concentration. Obviously, the input to calculating the rate for sulfur dioxide, we require the input for sulfur dioxide. So that's what we put here. And then for oxygen, we are going to put it here. Okay, we are saying that the reaction rate for the concentration of sulfur dioxide equal to this, that for oxygen equal to this, and of course, we are saying that reaction rate is equal to, it is going to be a float in 4 significant figures. So what else do we need? We continue and look at the range of concentrations. So we are going to also create an array using the line space function. So that is from the NumPy library. So they are going to be 100 points, data points, each starting from 0.01 to 1 and 0.01 to 100 data points for also concentration of oxygen. What you have to be thinking about right now, this is going to be a 3-dimensional plot because we have the concentration of sulfur dioxide on the horizontal, which could be in the x-axis, then the concentration of oxygen, which is in maybe the z-axis, and then in the y-axis, or whichever axis we have there, the rate of the reaction. So let's look at the two-dimensional grid of the concentrations. So we are going to use the function mesh grid, which is also coming from the NumPy library. So mesh grid of concentration of sulfur dioxide values. So we have already calculated them here. I mean, initialized them here. Then we have also for oxygen. The mesh grid is the one that is going to create a mesh that is going to be obviously in a 3-dimension plot. So we proceed and now look at the rate of reaction. So the rate values, we are going to again create another variable. So the rate values are going to be rate of reaction once we put in sulfur dioxide and that of oxygen. Those values have been created here. So let's look at now the plot. So plotting, we are looking at fig, which is equal to plot.figure, fig size is equal to that. So this fig function creates a new figure object for plotting. Then the fig size sets the size of the figure in inches, which is in width and height. So meaning the plot on which we are going to be having our, the figure on which we are going to have our plot is going to be 10 inches width and 6 inches high or tall. Then the axes what we are going to do is that this one is going to be specifying the subplot layer. So if it is specified the subplot layer, this one represents the number of rows in the subplot grid. The next one is represent the number of columns in the subplot grid, and the last one indicates that this is the first subplot in the grid. Then this other function, axis, plot, surface, we are looking at, okay, here the projection 3D indicates that the plot should be rendered in 3 dimensions. So when we come here, here we are setting up the color map, the color that we're going to be using for the this plot is going to be viridized. So meaning we are taking in the values of SO₂ from the mesh grid here, then O₂, the red values, and then we take in also the color map. Then we set the axis. So let's set the axis. And X, we are setting the X label, so meaning we are labeling the X-axis. The X-axis is being labeled with that, then the Y-axis is going to be taking the same function, but it will take oxygen instead. Then we're going to set the Y. Y is taking the concentration of oxygen. Then we need to put the Z. We need to put the Z. So this should be Z label. And this is going to be the rate of the reaction. And the rate of the reaction is moles per liter per second. And then the title is going to be the rate of sulfur trioxide production versus the concentration of sulfur dioxide and oxygen. So we save and then run this simulation. So members, this is how the simulation will look like. This is the mesh. Okay, we have created the mesh, and then you can see this rate of reaction depended on concentration of sulfur dioxide and concentration of oxygen. So you can see this is in 3 dimensions. We have X, Y on concentration of sulfur dioxide and oxygen. Then in the Z direction, you have the rate of reaction. So this kind of a simulation is very, very paramount when you're dealing with such complex scenarios that would require you to look at how fast you want to have your reaction, but you have a number of reactants that are taking place in that reaction. Thank you.